So welcome to this CAT class. It's the last time this semester. And the topic is topology optimization. If you don't yet know what that is, great, it's going to be even more exciting. So topology optimization basically is a function that can be realized with some of the commercial FEM softwares. It has become pretty standard during the last few years, and many of the modeling steps are identical with modeling structural simulations, right? So just when it comes to running the software, it should be not too difficult for you at all. Most of the steps are identical, you just choose a few different options. But logically what happens, or the motivation of this, is very different. Here, actually, today we're talking about a design tool, even more so than regular structural simulations, because what the software does is it creates a new shape. And this shape is the shape of an optimized structure, optimized with regards to the structural problem. That structural problem would be how much space you have for material, basically, which spaces you cannot change for optimization, what loads are acting, and then after all of that, the optimization goals that you define. That would be, for example, the minimization of weight. So basically, it's about saving materials and weight, but there are different targets you might have. You might set a specific maximum stress level, and out of that results, with a given load case, how light it can become. It will also become very flexible, which means the structure will be elastic but soft. It will be elastic because typically your stress level that you allow is, of course, within the elastic region of the material that you choose. If you don't want flexibility, if you want a stiff structure, you can define that too. But then, of course, you must exactly define how much weight you want to save. So Mahathep will go through these options and strategies. Before we go there, I would like to start with one application example that is pretty close to you. That was taken, we did this for a master thesis. That's already 3 years ago, it's amazing, from dear Julian Gavrisch. And basically the vehicle that you're seeing there, you've seen that multiple times too. I've been using this as an example throughout different courses. So this is our well-known Bangkok motorcycle taxi. So this is a small motorbike for 2 people. There's one sitting basically over the 2 rear wheels, and it's an electric vehicle, so we don't have an engine. We only have the motors in the wheels, but we do have quite a big battery pack. And of course, we need to create a frame structure. And because it's very different from established vehicles, we try to get an idea what an ideal structure is. So the battery pack basically is in the lower front region, more or less right behind the front wheel. So what you're seeing here is, of course, the vehicle suspension, and the purple block is what we call the design space. Now, that is the volume that can be used for frame material. Anywhere within the purple region, the solver is allowed to place material, with the exception of some areas, of course. So first we need to attach loads to that volume, and these surfaces that act as entry points for external loads are colored green here. That would be loads coming in from the front fork, from the front wheel, through the 2 bearings. So you see the 2 little rings on the left side. This would represent bearing seats. Similarly, the forces coming in from the rear axle act on the green ring on the bottom right end of this. And then we have Then we have an area which we need for the batteries. This is this red box inside. And then there are some surfaces where we want to have the weight of the batteries acting on. And this is really simplified. It could look completely different, but in this case, we decided only to have the small yellow patches in there. And then, of course, the main load acting on this volume would be, in this case, the weight of the driver acting on this little blue patch, right? So basically, in this case, we define the so-called design space as a CAD part, and the surfaces that we need to define constraints and external loads are just models, so it's pretty easy to pick them in the model. So here are the acting forces. Now the problem is, in most cases, that the acting forces are not always the same. Exactly with a vehicle, or especially with a vehicle, you might quickly forget that there are different driving situations where forces are completely different. If you just go with constant speed on a vehicle, you would say, okay, we only have the weight, mostly of the passenger and maybe of the vehicle itself, pushing it down, and then we have the reaction forces pushing up through the wheels and the suspension. But if you hit the brake, or if you accelerate the vehicle, the forces will be completely different. For example, if you do hit the brake, then the resulting braking force will basically push the wheels back, opposite direction of driving direction, and this would cause this moment acting here on the left top side, the forces D and E. So normally, it would just be the vertical force that you see here labeled with a little I, which is basically the reaction force from the weight of the vehicle acting upwards. But if we hit the brake, this weird moment between the forces D and E results, right? Also with the batteries, normally they just act as a weight pulling down. But if you hit the brake, of course, they will basically, the inertia of this mass will act as a force pulling forward, right? Now, if you don't take that into account, you will get a structure as a result that is great for static driving, but it will not react well to any other state of the technical system. So again, the hardest part of good modeling would be to come up with the different situations that are relevant for the structure's behavior and deduct from these simplified models, such as constraints and forces. In this case, this is put in, and this is the result that the topology optimization process, the FEM software, gives us. And it looks kind of neat. It looks like something that Swarovski might have designed. It looks very crystalline, and this, of course, is because it's using the typical mesh of an FEM model. So what the software does, it measures the design space as it would do with any structural simulation, and then these elements are more or less removed. Mahathep will talk more about this. And whatever remains are these little elements, and of course they have this facet surfaces, so it looks kind of weird. So you must know, when you talk about topology optimization, that it will give you a new topology, and topology means it's a qualitatively new geometry. So there are different structural optimization procedures like parameter optimization, but here we're really creating a new shape, qualitatively new shape, and this is why it's called topology optimization. But what you must be aware of is that typically the shape that is resulting from this FEM-based simulation or optimization run, this is not an FEM, not a CAD file. Often, or usually, it also doesn't consider other design constraints like production procedures. Although a lot of the new software have options like this, you can edit it. But again, I'm not a big fan of this. So typically the workflow is you run these simulations, then you understand the results, and then you redesign it in CAD, approximating whatever the FEM software came up with, and at the same time considering other constraints like what is possible with the chosen production procedure, could be draft angles, and so on and so on. So what you see here is already, you can tell it's this makes sense, right? What is interesting is that you have this interesting backbone, what I call it, this interesting shape. It's like a curved shape. And you have this big hole in the middle, right? So you have a typical frame structure. Could kind of approximate this with a welded frame, but possibly you'd come even closer with maybe cast shells on the top, and maybe together with profiles. But many weeks ago, I've shown you some images of motorbike frames, and if you go back to these, you would quickly get ideas how you would build a frame with this topology. What you also see is that there are two small belts at the bottom, one going down under the battery pack, one going to the front, really thin, because the forces resulting from the battery pack are obviously rather small. Now, this is an interesting looking result. It teaches us quite a lot. However, we still need material to encapsulate the battery pack anyway. This material will also have a weight, and it could also be used for structural purposes. So we run a second simulation where we told the software that the walls around this battery pack must kind of remain. This will give us maybe a similar shape, but something that includes the box. What I just realized, what I should have pointed out more clearly, is another very important force resulting from the rear wheels, and that is, these are of course the forces coming through the shock unit, right? So of course a few slides before that, that would also be a surface that must remain. So this is something you define, surfaces that just have to remain anyway, and then you have surfaces where you have constraints and therefore forces acting, and they will typically remain anyway, because if you have this force flow, this is where you need material to support this force flow. So this is the result of the second simulation, where we define that we want material to remain as walls for the housing for the battery compartment. And it's not really surprising, the result that we get here. We still have basically the same shape, the same backbone, although it's kind of flatter in this case. That might really be because now the lower portion of the resulting shape contributes a lot more to the structural function, to the stiffness of the frame. Okay, so that was just an introduction example. Mahathep will demonstrate this example, what you're seeing right now, which is a bit more basic, and it's always good to start with basic problems for simulation, because there are so many things that can go wrong, and the bigger the model is, the longer it takes you to find out why it's going wrong. So this is today's demonstration example. Pretty simple structure. Basically, it's a bending beam. It's a flat strip of aluminium attached to the wall at the rear end. There's an external force pulling it up, 500 Newton. And for the optimization, the gains or the parameters of the optimization that Mahathep will explain to you how to set them will be to minimize the mass. So there's no specific mass, target mass, and this is possible because the maximum stress is defined. In this case, 200 megapascal. And there's also on top of that maximum vertical displacement defined together with the external force. So also just so you can expect what you're looking at. Basically, the first step, you will run a regular linear static structural analysis as a bending beam. You will see, you can already estimate how this thing will react. You will see what stresses and deformations will result with the unshaped geometry. And then after the optimization, you will get a pretty interesting shape. I have to say, it's basically a two-dimensional node case. And there will be maximum stresses according to what you allowed. And again, there will be some derivations. So this is going to be example, and I will already mention what your assignment will be. And you could say it's basically the same, but it seems more complex, but the work steps are very similar. So the assignment will be for everybody to find a new topology for the rear part of the frame of the rickshaw. So I gave you a hand sketch of how I would define the design space. And that is a very blocky piece of steel. You will use the same material that you expect for the final design. And I would define separate surfaces for the seat, for the footrest. Keep in mind, people will step on the footrest to get into the vehicle. So it would be a typical design mistake to assume only the low forces when seated. You must put there the pretty high forces that will happen if somebody steps into the bike. So probably you would try to step in with 1 foot, then 2 feet, then turn around, sit down, right? And then in the rear end, there's also a surface for the cargo space. In that little photograph, you can tell you might have like some sort of container or support. You should also maybe put on some volume on the sides that will take the wheels a bit further away. Now, I haven't given you any dimensions, partly because finding out about the dimensions is really important for your design project. Also, I don't really care about the dimensions here too much, right? So the result will be something that will contain mostly of very thin, long sections. And this would give you an idea if you design this as a steel frame made from tubes where you should have the tube. Okay. The maximum stress here is only 100 megapascal, so roughly half of typical yield stress. I would do that kind of conservatively, right? Also because you have to redesign it later with tubes anyway, and you have to rerun the simulation anyway. Okay, so with this, I hand this whole thing over to Kun Mahathep.
Thank you, Dr. Alex. I will share the ANSYS workbench, and today we are gonna do the topology optimization of the part that Dr. Alex mentioned previous. The first step, we will do the static structural analysis for this part, and I will open the workbench ANSYS and click to open the static structural module. Yeah, you can double click or drag it to the project. And the first thing, I will change the unit. In this case, I use the metric unit, right? And we will assign the material in the engineering data here. Right click or double click to open, and click the engineering data source here. And in this case, our part is aluminum alloy. Aluminum alloy is in the general material. Click in the general material and find the aluminum alloy and add it to the library here. And we turn off the engineering data source. You will see the aluminum alloy available in your engineering data. And after that, close the engineering data and draw the part. In case of you have a model, you can import it here, but Today I will draw a new part. There are two CAD programs in the ANSYS workbench. The first one is a new space-cam geometry, and the second one is a design modeler. At the static section, I will use the design modeler here. When you open the design modeler, we will see this screen, and I select the XY plane to as a drawing plane and click the new sketch here. And I change to sketching mode here, adjust the viewpoint to the normal to the XY plane, and click the rectangular to draw the main shape of the part here, and click the dimension to give the dimension to the part here, and the vertical dimension. Okay, and here you will see the dimension at the left side, and you can change to into the design dimension in this case the horizontal is 200 millimeter and the vertical is 50 millimeter. Okay. And I will draw a circle here. Okay. And change to the dimension. Give it a diameter and assign the vertical position and horizontal position. Yeah. Change it. And for diameter is the diameter of the hole is equal to 25 millimeter. I'm sorry for the wrong number here. Okay, the other dimension is correct. And from the drawing, this part has a thickness equal to 10. I will use the extrude here. And we select the sketch and apply it to geometry and assign the depth and click generate. Okay, now we will get the solid part here in the design modeler, and we can close it. You can close it. Just, we will open the model to assign the load and do the analysis. You can right click in the model and edit here. Okay. Okay, first we change the unit. Make sure that it's correct. Okay. And you assign the material to the solid part by clicking here in the material and clicking here. And change in the detail in the material. Assignment, right click here, right click and change it to aluminum alloy. Right. Okay. And we will do the mesh. And in this case, I will use the mesh size to control the mesh. The way to do is you click in the mesh here and click mesh control here and click sizing. Yeah. And after that, you select the whole part here and assign. And you can control element size by insert the number, the size of the element directly here. I will use 4 millimeter. Check it. Right click and generate mesh. Here. Okay, it looks good. And go further to the static structure. I will assign the boundary condition. The first boundary condition is a fixed support at the right end. Here, you can right click here and find the fixed support, or you can click down here to the fixed support and select the surface here and click apply. Okay, you will see it's fixed. And load, in this case I will use the load type to the bearing load. Yeah. Okay, by right click, insert the bearing load, or click here, it's the same, and select the surface, the whole surface, apply it, define the magnitude of the load and the direction. I will use the component function. Okay, assign 500 Newton in the y axis. Okay, the graphic will show the red surface with the red arrow that illustrates the direction of the force acting on the part. Okay, and we finished the setup of the load and boundary condition and can solve it. Okay, and we want to see the stress, how much stress that the part resist. In this case, you can click here to the solution folder here and select the equivalent one stress and do the analyze. Yeah, you will see the stress occur in this case. For the displacement, in this case, we want to know the displacement at the center of the hole, right? And to define the center of the hole, we will use the remote point. We will construct a point here by first we select the model. The taskbar will appear here, and you will see the remote point function. Click here, and the remote point we will select the surface here, apply, and it will generate a point that position in the center of the hole, and we can use this point to analyze the displacement by click the solution function here and click down the probe function and the deformation here, and select the location method, change the location method to remote point, and select the point name. In this case, I didn't change the name of the point, it will remain the remote point here, and we stop it. Okay, it's shown the result. Yeah, the left side here is 0.12 millimeter deform in the y-axis. Yeah. After this, I will close the static structural analysis to do the topology optimization. Yeah. Back to the workbench. Look at the left side, you will see the topology optimization module here. And you click and drag down, sort out the static structural. Yeah. If it's correct, it will contain 4 links. First one, engineering data. The second one is geometry. The third one is model and the solution. Okay. And I will open to do the topology optimize. Edit here. Okay. The topology optimized window look like this. The first thing I will check the optimization region here. Normally, ANSYS will generate the region that allows to remove or do the optimize based on the boundary condition. You will see in this case, there are 2 boundary conditions. The first one is a fixed end, and the second one is the load surface. These 2 surfaces will not allow to remove or to cut the material. Yeah. But if you want to redesign or edit, you can manually select here. Okay. After check the design region that the program can remove the material, is it correct? Is correct, and we will do the next thing is objective. In the objective, I want to reduce the mass. I will change the response type to the mass. Okay. The first one is a compliance of the static structural. It will try to minimize the stress based on the previous analysis. In this case, static structural. In this case, I want to minimize mass. I change the response type to the mass here, and set the response constraint according to our problem. The constraint, the first constraint is a maximum stress. Global bonding stress. Should be not more than 200. Yeah. And I can add the other constraint by click at the topology optimization folder and right click here and insert. And insert the other constraint like displacement. Here, displacement constraint. In this case, I want to control the constraint at the center of the hole, right? But we cannot select directly at the point. We have to change it to the name selection. You can do by click here to remote point here and promote to the name selection. Promote to the name selection. It will appear the name selection of the point here. And for now, you can select in the constraint name selection to remote point to fix it. In this case, I not allow it to displacement over 0.5 millimeter. Yeah. And I will add another constraint like a manufacturing constraint, such as the extrusion. This extrusion function is a constraint that helps and useful for when we manufacturing it. I do the x-axis extrusion. It means that the cross section of the optimization geometry will consistent in the x-axis, like you extrude it through the extrusion die or a process. Yeah. Also, you can change the extrusion direction. The cross section of the x-axis will remain consistent and the same. Yeah. Okay, and I think it's finished here. You can click solve. The calculation will take time around 5 minutes. Sorry, what is constraint? X. There are a little bit problem here. Let me show you the complete topology optimization. Yeah. The program is running and it takes time. Okay, it's finished. And at the first time, I cannot solving because of I set the wrong constraint, manufacturing constraint. Here I use the X direction. Yeah, and it's if it's correct, it has to set to the C direction here. See, okay, and so I skip this function and I reanalyze again, and this is the result you can see here. This look not good, right? But you can select the retain threshold to more conservative to produce. Yeah. I cannot tell you how much the return threshold is suitable for the parties depending on your design. Yeah. And in this case, I select around 0.2 here. Okay, and I will close this to do the another validation process. I will do the another static structural by clicking at the result of topology optimize and transfer to design validation system here. Okay. The another model will appear at the right side, and at this step, you have to click at the result, right click, and update it. Okay. And again, click at the geometry. Here, right click and refresh. In this case, I will rebuilding the optimization part from the results of the topology optimization by the SpaceCam modeler. Here, and edit geometry in SpaceCam. Okay. In the SpaceCam modeler, you will see there are two parts. The first part is the original part here, and the second part is optimized part. You can turn on and turn off to see which part. Okay. In this case, I will turn off the original part and I draw it new part. I click the sketch mode in the design mode here and select the surface here. Okay. And after that, I drag the left mouse, left click here, select all of the line and copy here and paste it. Okay. For now, I got the line, the projection line. Okay, and I turn the optimize path off, and I reconstruct it by manually. Here, I select and delete it. Okay, and construct it. Here, I trim it off in this way to make it more beautiful. Yeah. Okay. And repair the all of the line here, repair and complete. Here. Okay. And after you modify to achieve your desired, and you can match the solid part by the pull function here, and click here, and click it again, pull it both sides, and hold the left mouse click and assign the ticket here. 10. Okay. Okay. And you will get the part based on the optimization part. I will turn the surface off here and modify the shape in the pull function here. Okay, and I will sublet all the other part here. Click the original part, right click and sublet for physics here. Sublet for physics here and sublet for physics. It means that the other part will not transfer to the static structural here, and you close it and do the analyze, the static structural analyze. Okay. Okay. When you open it, the part will import it. And again, assign the material, luminous oil, and remote point. So remote point 2, and sublet here. Please select the point and please select the body here. Click on the body sizing in the main function. Okay, and generate mat. Okay, and assign the boundary condition again here, and value load here, and for the deformation, go reselect the remote point by create another name selection and sorry, select form here, promote to name selection. Okay, remote point to. Okay, for the formation probe, you can select remote point to. Okay, and do the analyze. Okay, as the point, I get the new part, optimization part, based on the constraint that we assign with the equivalence stretch not more than 200 megapascal, and the deformation probe show that the deformation maximum in the y-axis is equal to 0.2 here. And you can compare with the previous one by this result. Okay. Yeah, this is the previous design, so original design, and okay. Dr. Alex, I already done the demonstration of the redesign part. Okay.
So looks great. I was surprised to see this last bit of the process where you take the optimized shape, tweak on that, and then rerun that again, but it makes sense. Now I'm personally a bit worried that the assignment I gave to you will be a problem because the number of elements is limited, right? So in any case, the mesh for your design space will be pretty coarse, right? Very rough. So the results can also only be rough, right? So, but I mean, that's no big deal. I'm aware of this limitation. So it was just an application example that seemed reasonable to me. So just try to get as many elements as your license allows into that design space, and then let it run. Normally, I would expect pretty thin, long structures there, but again, the element size will probably not allow that or limit that. And see you soon. Bye-bye.
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 Bye-bye.